Adrian Finch is Professor of Geology at the University of St Andrews, specialising in mineralogy, petrology and geochemistry of rift-related magmas. His research focuses on describing the mineral deposits which form in rift environments, which include rare earths, niobium, hope I said that right, and tantalum, hope I said that right too. Got a thumbs up. He works by explaining the shape and grade of the deposit and by developing models of how they formed. He's worked on alkaline rocks from all over the world, from Mongolia to Malawi to Greenland, with a particular reputation for fieldwork in the Arctic. And the title of today's talk is The Challenges Facing 21st Century Critical Metals, from Mantle to Mine to Magnet. And I'll pass over to Adrian now.
Okay, well, thank you, first of all, for the invitation to come and speak to you all. I presume that you can hear me okay and you can see my slides. Just give me a thumbs up if you could. That's good. Right, excellent. So what I'd like to do in this talk is to really provide a geologist's view. Hang on, my slides are not working. Of some of the debates that we have here. And I'm going to start with the geology bit, which is how rare earth deposits form in the Earth's crust, how we can find them, the way in which we can track them down. Then I'll start to talk a little bit more about the way in which this type of exploration for very rare elements such as neodymium, niobium and so on is at the heart of really some of the discussions about green technologies. And this has been particularly important given COP26 just along the road from here, talking about very much about how we're going to develop into a world which doesn't have such a reliance upon oil and gas, but really what that means in terms of green technologies and the opportunities for the development of green technologies and exploration in the future. I'll make some comments about our position within Europe and whether Europe has the potential to become self-sufficient, not just in the use of critical metals, we're very good at using these things, but actually producing them and contributing them to the global economy. And finally, I'll talk a little bit about how we can find ways to minimize the carbon footprint of critical metal production. And throughout all of this, I'm going to talk generally, but also I'm going to use this as an opportunity to tell you a little bit more about the type of research that those of us in Earth and Environmental Sciences within the school here in St Andrews are involved with. And I'll talk a little bit about my own research, but I'll also make reference to that of my colleagues. So the first thing I'd say is that modern technologies surround us all the time. And with regard to climate change and many of these carbon-free green futures, we're talking very much about things like electric vehicles and things like wind turbines. But actually, these modern technologies have permeated all of our lives. I'm sure you're not particularly far away from your phone, wherever you're sitting now. That particular technology has transformed our lives, but also it extends to medicine. And if you've ever been to hospital and been connected to the machines that go ping, then you're surrounded by a whole suite of modern technologies, which are in turn dependent upon the supply of a whole range of natural materials. And anyone that's ever been in a MRI, for example, here on the bottom right, has been surrounded by 1/2 ton of the element niobium. And part of my research is finding out more about where that niobium comes from. In this case, it comes from one mine in Brazil, and trying perhaps to find other places where we can extract and make use of these materials. So what's the history of extraction? Well, if we project something simple like iron ore, the amount of iron ore that we've extracted in the world going back in time, we go back 50 or 60 years, we can see that over time, our demand globally for even some quite common resources such as aluminium or iron have expanded year upon year. And if you eyeball up some of the values there, you can see that the demands for iron ore have increased over 50 years by something like 5 or 6-fold. And the same is true for almost every natural resource. In fact, demand for natural resources, even the simple ones such as iron and copper, go up year upon year. But what's of particular interest to me are some minerals and some elements which are relatively rare. And if we take the example here at the bottom, in purple, PGM stands for platinum group metals. So things like platinum, iridium, rhodium, these have gone up year upon year. These are used in car catalysts, the catalytic converters in your cars. Lithium is becoming more and more important as we go to rechargeable batteries. And the very notable inflection that one observes here in the red line in the tantalum extraction is due to the development of mobile phones. And tantalum is used as a capacitor in every one of the mobile phones that all of you have in your pockets right now. And this very, very notable inflection is really a consequence of the expansion of that type of mobile phone technology at the turn of the millennium. So this tells us two things. One is that, of course, demand for everything is increasing, but it means also that there are some elements which suddenly gain particular interest or prominence as a technology is developed which is dependent on them, and then tantalum is a good example. So we've got two things here. One is that things are changing, the values are going up, but that's not the whole story. In fact, the whole story is that year upon year we're needing access to more and more elements. So when I grew up in the 80s, my parents lived a reasonably good life, and they had access to something like a dozen natural metals to live that life. And then as time progressed to the 90s, we had 4 elements as well, which became integral to part of our modern life. But at the turn of the millennium, with the development of many, many more technologies, which are in themselves dependent on access to other parts of the periodic table, then suddenly modern life became dependent not just on a handful of elements, a handful of natural resources, but on access to almost all of the periodic table. There is almost every element in the periodic table that underpins some aspect of our modern lives. In fact, there are fewer elements that we don't need access to live the modern life as there are elements that we do. So the story here is one of not just increasing need for elements, but it's an increasing and ever expanding need to access rare and unusual elements, which often have applications in particular technologies. So the challenge that faces me and my colleagues here in Earth and Environmental Sciences is to find new sources, not just of rare metals, but indeed all metals and most resources. And the key thing here is that we're meeting not just an ever increasing demand, but we're having to move and respond quickly to when technology provides us with a demand for something we'd never thought of before. And there is an increasing need for a wider range of rare elements, not just for the very unusual applications, but actually for modern everyday applications in modern life. And what's notable to me as a geologist, and many of my colleagues will agree with this, is that we're hearing a great deal coming out of, for example, the COP26 meeting, where we're talking very much about targets for electric vehicles. So perhaps by 2030 or 2050, we believe that much of Europe will have gone over to electric vehicles. But as a geologist, what strikes me is that implicit in that are dramatic increases in the need to find the metals and other resources which are used in those green technologies. So I contrast the many sweeping commitments that there are to green futures with the very few commitments that I can observe that are being made to actually find the resources that are going to be necessary to make that happen. So as I go forward, the thing that strikes me is that I can see coming on the horizon a great need for people such as I that are involved in the development and the exploration for these new resources. So I can contrast that sort of vision that we have with some of the language which came from COP26. Here's a few quotes from there. So Greta Thunberg, in her own way, said, "No more exploitation of nature and the planet. No more exploitation, no more blah, blah, blah." And okay, so Greta was outside the main auditorium for much of the discussion, but here's the UN Secretary General saying enough of drilling and mining our way deeper. We are digging our own graves. And what strikes me and many geologists in this is the disconnect that there appears to be between, on the one hand, people committing the planet towards a green energy future, and at the same time assuming that, or the message that seems to come from this from many people in the same auditorium, is that there is some kind of pushback against the finding of natural resources. And what I would say is that the future that we anticipate, these green futures based on electric, which is coming from renewable sources, implicitly has within it a demand to mine and to extract some of these green e-tech metals. Okay, so this is an opportunity then for me to explain what my research is about and to give you a flavour for some of the issues which we address to achieve these goals. So I'm interested in finding new rare element deposits, and to do that I have to be a volcanologist, and that's because these types of rare elements were formed, or they were concentrated to make mineral deposits underneath ancient volcanoes. And the research that I have, and many of my colleagues, is to understand those deposits, how they formed, how we can get the most from them today, and also to develop pointers that could allow us through exploration to find other similar deposits elsewhere in the world. So actually, strangely enough, although my objective is to understand and to provide the world with more resources, actually that involves me in studying volcanoes. So here's a picture of a volcano in Tanzania, which is well known to many geologists, called Oldonyelengai. And we know from the material that's being erupted at the top of this that there is a very unusual magma type existing beneath it. So the volcano on the top is really the surface expression of a crack in the Earth's crust through which liquid is moving up and erupting. And it appears on the Earth's surface. And with time, we build up a big pile of this material which is now the volcano. And if we think about what's underneath it, then we can infer from the material coming out of the top that there must be some magma chamber, some volume underneath the chamber which is full of this unusual liquid, and that it is finding its way through conduits and cracks in the Earth's surface up perhaps a distance of something like 3, 4, 5 kilometers up to the Earth's surface where it is erupted. So we know that there are processes. We have the magma chamber at depth beneath this volcano, and we know from analogies elsewhere that presumably similar ore deposits, rare earth bearing ore deposits, are being formed underneath the chamber. And this leads me on to a very important point, which is that although we have reason to believe that today, underneath volcanoes such as Oldonyelengai, rare earth type deposits are being formed, the important thing is you can't pop down and have a look. So we know or have reason to believe that these processes are taking place, but we can't study them in real time. And I remember when I was one time, and parents out there will remember, will sympathise with this. There's one time when my daughter was off school and I had to give a lecture, so I put her at the back with her drawing things, and I gave a lecture on critical metals to the undergraduates. And when I came back, she'd drawn a picture for me, which is this one. And it was expressing very important point number one, which is that you can't pop down and have a look. And what it's showing is some two rather ill-informed geologists attempting to study mineral deposits by being lowered into the mouth of an active volcano. And I can't read the voice bubble here, the speech bubble here, but I suspect this is a geologist expressing his regret at attempting to study mineral deposits in this way. So the far better way to study things is to find volcanoes which are now extinct, which are many millions of years old, and ideally where they've been uplifted so that the top 3 or 4 kilometers of the volcano have been eroded away, scraped away. And what we're looking at is what I would describe the pipes, the conduits underneath the actual volcano itself, what I've here described as the plumbing system. And it's here in these plumbing systems that rare earth deposits are formed. So underneath Alduin-Yalengay now, we have reason to believe that the rare earth deposits of the far future are being formed, perhaps 100 million years in the future. But clearly we can't study those processes in real time. So very important point number one, you can't pop down and have a look, leads me on to very important point number two, which is that rare earth deposits only exist when there's a particular geological recipe. And that has to be where there is some form of continental rift, which has a series of volcanoes along it. Now we know they must have existed and been active in geological time, but now they're extinct. And what we want is some form of erosion to have removed the top 3 or 4, say, kilometers of the surface system above them, allowing us to access and see the plumbing systems beneath them. And this is where the mineral deposits are found. And there's a certain amount of Goldilocks in this, because if we erode too much, then we rub away and remove the entire deposit we're looking for. And if we erode too little, then the deposit remains some kilometers below our feet and we can't access it. So we need a real constellation of events which aren't entirely frequent, which is why many of these metal deposits are rare things. But it's occurred sufficiently frequently in geological history that there are many examples of where this constellation of events has been met. So in Greenland, in Scandinavia, in Africa, in Asia, countries like China, for example, these events have taken place, and we know that rare earth deposits exist within these countries. And the general output of this type of research, they can be summarized in diagrams like this, which are conceptual models of the way in which the volcanic structure worked, the volcano was working, and the relationship of the processes creating the rare earth deposit and the critical metal deposit to the overall magmatic system. And this is the type of research that I and my colleagues are involved in. Okay, so let me focus in on one particularly important natural resource, which I think is quite critical to some of the green technology futures that we've described. So the rare earths, you hear a lot about them, they are described as some of the world's most critical natural resources. And to illustrate this, they're used in electrical vehicles as part of the motor system. They're about 1/2 ton of neodymium is found in the magnets of wind turbines, for example. And here is an analysis, it's a few years old now, from 2017, of the European Union's assessment of its natural resources. And it's a graph of economic importance on the bottom here in units, which I'm not really going to discuss, against what is described as the supply risk. And where we have elements or groups of elements coming from single places on the Earth, then that's considered potentially to be a supply risk, especially if that government that owns that resource is not necessarily favourable to the West. And so hence here, right at the top of the list, are rare earth elements. And it's because most of the world's rare earths are coming from mines in China, 1 or 2 super big mines in China. And the Chinese government has introduced export quotas on material it's exporting to the remainder of the West. And if companies want to get around these quotas, then they can simply relocate to China and therefore be secure. And that's causing something of a technological brain drain towards China. So this idea is that many resources, okay, we need more of them, but many of them are described as critical. And what that means is that we're strongly dependent on the delivery of those resources from one place. And if that place were to change, if the political governments were to change, then we might find ourselves in a position where we simply cannot access them at all. So this is the concept of critical raw materials, where one supplier, one country has control over the whole global market in a particular resource. And in the case of the rare earths, these are technologies, these are materials utterly critical to the development of many of the green resources and green technologies that we've been talking about in recent discussions. So what are the rare earths? Well, there are a whole family of elements. There's, depending on how you define them, there's anything between 13 and 15 of them. And they're divided up into two groups. There's ones called the light rare earths, where the atoms are relatively big, but they're not quite as heavy. And there are others called the heavy rare earths, which are a series of other elements, which are very similar geochemically, but actually have slightly smaller ions and they have slightly heavier ions. And all of these elements are found together in nature. They hang around together. They're geochemically so identical that where you find one, you find them all. But what's interesting is that the ones that I've labelled here with a series of yellow circles are ones for which there are particularly notable technological uses. And the neodymium here, Nd, this one is the one which is used in turbines and in electric vehicles. It is often alloyed with some of the others. So Tb is terbium, dysprosium is Dy, and gadolinium is Gd. These are also used in those magnets. And others such as europium and gadolinium are used in phosphors. Erbium, I believe, is used in phosphors as well. And ytterbium over here and yttrium are used in different, they're used in alloys. So the key thing for us here is that we get, whether we like it or not, we get the whole package. We get all of these rare earths together, and we have to separate out afterwards the ones that we actually want for these devices. But the key point is that the two most abundant ones are lanthanum and cerium. And they do have applications, but they're not such a problem. They're effectively not quite worthless, but they have very few applications compared to the others. So where are the rare earths coming from? And as I hinted in the title, the ultimate source of these things is the Earth's mantle. So a magma, you have some form of process which generates magmas in the mantle. These rise through the Earth's crust, and as they rise, they evolve, they change their compositions. I can talk more about that at the end if people are interested. And we end up with the development of a volcano on the Earth's surface. And that's the sort of thing that we see here at Aldin-Yellengai. There are two different magma types which follow this journey, and each of them are important to us. One is called carbonatite, and the other one is called what I'm going to describe as alkaline igneous rocks. And all of the world's rare earth deposits come from these two deposits, these two magma types, carbonatite here and here, or things which have been generated from these rocks. So in some cases through erosion, we can generate mineral sands from them, and through formation of soils on top of or near some of these rock types, we generate what are called ion absorption clays. So we have four main rare earth deposit types. Each of these are either generated by magmas or from the erosion of them. And if I take this review article here from the literature, which looks at the distribution of potential rare earth projects across the world, you can see that they're not randomly distributed. They appear to be focused on particular regions, and a geologist looking at this map would recognize that these regions are some of the oldest parts of the Earth's crust, what we call the cratons. But there's quite a few projects here. It's not that rare earths are genuinely focused only on one part of the world. Actually, there's lots of them all over the place. So there's a distribution of potential rare earth sources across the whole planet. So what's the best recipe, if you like, for the perfect rare earth deposit? And you'll remember that I said to you that this is not a single resource. It's a whole family of resources. And we have these two rock types that generate them. And what's quite interesting is that the proportion of light to heavy rare earths is very variable between these two rock types. So if I take the carbonatite type, for example, neodymium is used in these magnets. I can see that the carbonatite type deposit tends to have something like 1 or 2 orders of magnitude greater abundance in carbonatite than we find in the other source, which is the alkaline igneous rocks. So for neodymium, I would be going to a carbonatite type mine to extract that. But conversely, the dysprosiums, the erbiums, the thuliums, all of the other heavy rare earths, these are far more abundant, again by orders of magnitude, in the other magma type, the alkaline igneous rocks. So what's important to take away from this is that any future extraction, any future plan, if you like, to extract rare earths from the crust must involve not just the analysis or mining of one rare earth type, one magma type, either carbonatite or alkaline igneous rocks, but it is likely to involve a combination of exploring carbonatite in some places and exploiting alkaline igneous rocks in others to provide us with the light and heavy rare earths respectively. The other key point to take away from this is that many people, when they describe the value, if you like, of a particular project or a particular potential mine, use what's called total rare earth content. And you'll notice that the vast majority of these rare earths are lanthanum and cerium, which don't have very much value. The one that we're interested in is this one here, neodymium. So the total, most of the rare earths that you dig up, possibly 90 or 95% of that, depending on the rock type, is not of value to you. You're interested in, let's say, 10% of the actual thing, which is neodymium, which is what you're after. And the others, you have to extract them because they're geochemically similar, but then you have to invest a lot of money in separating the neodymium from its other brothers and sisters in the rare earth sequence. So total rare earth value is often not a good indicator of the value of the resource to us. So this idea of the proportion of heavies to lights can be expressed in this type of diagram here. Carbonatites with the lighter color are dominated by these light rare earths. They can provide us with the world's neodymium, but it's these other alkaline rock type deposits which are likely to provide us with the world's heavy rare earths going into the future. So any sort of planned exploitation of rare earths is going to include a combination of sources, not just one particular mine providing all of the world's rare earths. So that's one aspect. The other aspect we have to keep in mind is that many of these rocks, these carbonatite and alkaline igneous rocks, are also radioactive. And it's just the fact that the processes which generate rare earth rich rocks can, in some cases, also generate uranium and thorium rich rocks at the same time. So if we take some minerals which contain rare earths, such as monazite or xenotime, we can see here on this graph, this is a log scale and this is the radioactivity, that some of these are highly radioactive materials. And what that means is that if I take some xenotimes, for example, and I extract the rare earths from them, then I would end up with tailings which were exceptionally rich in uranium and thorium and highly radioactive. The uranium, you can in principle pass that on to the nuclear industry, that could be used, but the thorium, as far as I'm aware, totally useless. So it would end up as a tailing. So the extraction of rare earths from these types of deposits is fraught with difficulties. And we can contrast that with the amount of radioactivity in minerals such as eudialyte, which is expressed here, which is far, far, far lower. So the exploitation of which mineral is very, very important. Otherwise, we can find ourselves having byproducts of very large amounts of thorium, which then effectively becomes a radioactive waste. So this is a key issue we have to keep our eye on. But in addition to that, we have to have minerals for which there is a clear track record of success. So the key point here is that we're looking for some kind of processing, digging the mineral up, crushing it, separating out what we want, dissolving that away into solution, extracting the rare earths, and then separating the rare earths from each other. We need to do this in the minimum number of steps. And, we need to separate out the physical rock that we're interested in from other rocks that just happen to be around. And we need to do this in a manner which doesn't produce toxic tailings. The simple fact is that for many of the minerals that we're talking about as potential suppliers of rare earths going into the future, we don't have a successful track record of extraction for them. So if I look at the next slide, so we've extracted rare earths historically from minerals like monazite and xenotime, which are radioactive. And as a result of that, rare earth extraction in history has generated radioactive tailings. We clearly don't want to be doing that going into the future. But it means that our known, if you like, proven track records are against a set of minerals here, including bastnäsite and apatite and loperite. We think we can probably extract rare earths from sintersite and parisite by very, very similar methods to bastnäsite. That seems to be quite logical. But many of Europe's resources are in minerals like ansolite and eudialyte, for which there has never ever been a successful exploitation or extraction plant built. And the key point that I would make is that much of the resources, much of the future going forward here is being funded by private enterprise. And if you're an investor, it's very difficult to invest in something where you don't necessarily have 100% chance of success. It's possible that actually creating a plant to process a new mineral might come across some kind of hiccup. And so the investment to crack that problem hasn't so far materialized. Okay, so we've got three issues there. One is, where are the resources? The second is, are they associated with uranium and thorium? And then finally, is there a known process to extract the rare earths from the minerals? So let me ask a question. Does Europe have its own rare earth deposits? And if I zoom in on that particular part of the map that we looked at before for Europe, you'll see that the answer to that is yes. So Europe has deposits in Sweden, Norway, over here in Greenland, for example. These deposits over here are in Russia, and for Russia is strictly European, I guess, in its geography. But in terms of political alignment, it's not considered by the West to be, by the European Union at least, to be a friendly country. So we kind of forget about that. And what this demonstrates to us is, yes, we do have a crop of potential rare earth projects sitting in Scandinavia and Greenland. So this is an opportunity now for me to tell you a little bit about my research. And if we pop now to the south of Greenland, we'll come to a particular part of the crust there. And southern Greenland is made up of a series of what we call geological terrains, each of which has a slightly different geological history. So we have the original oldest part of the crust, the Archean craton, and then we have a series of rocks which were attached to the craton around about 1.8 billion years ago, called the Ketalidian orogeny. And it's thought to be an Andean type margin. But what's of particular interest to us in terms of the resources are what we call the rocks of the Gardar province, which is shown here in a sort of dark browny colour. And these are, as I suggested, the products of a failed continental rift. So this is an example of a continental rift which had volcanoes across it. If we'd been there 1.1 billion years ago, it would have probably looked much like modern East Africa in its geography. And there are examples of erosion here which have taken off the top 3 to 4 kilometers of material, giving us that perfect horizon at which we can study the mineral generating processes. So here amongst the Garda province, we have a variety of different projects going on, and there's a lot of exploration associated with the Garda. And let me take you and show you 2 of these that we've worked on here at St Andrews. The first one is a place called Motzfeldt, and it's actually one of the world's largest tantalum deposits. And you'll remember that tantalum is used in mobile phones. There's some geological comments there. The high field strength elements, in other words, the tantalum and the niobium, are found in a mineral called pyrochlore, and it's got a very complex geochemistry which we've studied. We can take the whole Motzfeldt area and create a map, and this is a map which is partly from the literature and also partly supplemented by our own research done in the area, and we can generate a structure to the intrusion and work out which parts have taken place where. And we can actually go and visit the area, and this is what that sort of area looks like. And to give you some sense of give you some sense of scale, this just down here in the bottom left of your field of view is a little bit of ice on some water. Don't know if you can see that. That's at sea level, and the top of that mountain there is 1.5 kilometers high. So you've got a cliff here which is 1.5 kilometers vertically straight down. And as a geologist, what really excites me about these types of terrains is they provide us with genuine 3-dimensional slices through the plumbing systems beneath old volcanoes. And we think this is the top of the magma chamber here. We can see that there's what we call the roof zone, in which many of the mineralizing processes have taken place. And we have another rock called nepheline syenite beneath it, which is less highly mineralized. And from places like Motzfeldt, places with these wonderful 3-dimensional slices, we can generate cartoons such as this, which place the mineralizing processes within an overall construct of what the shape of the magma chamber looked like. So the key thing to take away from this is that we use places like Greenland with these remarkable 3-dimensional slices through structures to tell us about processes which are happening now as we speak underneath volcanoes such as Alder and Yellenghi. So Motzfeldt's the first place which I'm going to take you to. Let me take you to a second place called Illimausak. And this has one of the world's largest rare earth deposits. And actually it's divided up into 2 separate tenements or 2 different licenses. And the elements that we're interested in here are found in the mineral called eudialyte. There's also some called steenstruppine, but eudialyte is the primary target. And this is a geological map of that. And all of the colours that you can see here are different forms of magma. And what we can see here is the remnants of a magma chamber which has been lifted up. All the top has been scraped off of it so that we can see the plumbing systems and the magma chamber systems beneath it. So these are 2 of the world's largest deposits. The top part is called Kvarnefjell, and that's licensed by a company called Greenland Mining Minerals and Energy. And here we're using the mineral steenstruppine. And at the southern end of this, we have a project called Kringlerne, which is owned by a company called Tanbreez. And here they're looking at zirconium, niobium, tantalum, and rare earths. So this is what this field looks like this is what this area looks like in the field. It's uninhabited. It's an exceptional place. It's genuinely a stripy mountain, and unless you've seen it, it's really difficult to believe quite what you're looking at. But those stripes, each of those is something like 10 meters thick. So we're using rocks which rejoice in the name of quartzite. Don't worry too much about that. And each of these layers can be tracked across the landscape. And the resource holder, Tanbreez, estimate that there's 4.3 billion tons of ore there containing percentage levels of zirconium, niobium, and a certain amount of rare earth as well. But remember that this is an alkaline igneous system, so it's enriched in heavy rare earths, which are quite valuable. this is what these layers look like in the field. They're quite remarkable. And the rock that we're interested in, the material we're interested in to extract, is this red stuff here. So this is a sort of another view of the same stripy mounting, and the project owners have already put forward a vision for how we can extract this material, process it, store it. And one of the benefits of Greenland for this sort of project is that these fjords are exceptionally deep, which means that very large boats can come very close to the shore and be loaded with some of this material to be taken away for extraction. So the answer to the question I set to you, does Europe have its own rare earth deposits? The answer to that is yes. And we have, in fact, deposits which are so large that in principle they could accommodate almost all of global demand. So we're not short of our own resources. But in many ways I should have asked a different question, which is that does Europe contribute anything to rare earth production? And the answer to that is no. There are two reasons, one of which is geological and one of which is political. The geological one is that the minerals that we're hoping to extract don't have a track record of extraction before. And therefore it's very difficult for us to get private investment to come in and get over that hurdle. This is something where governments might have stepped in. But actually there's a political reason to this. All of these projects have been stopped because of local objections, even in places where there are actually very few people living there. So in Greenland, for example, there are very few people that live anywhere near these mines. So we have here, the key thing is that nobody wants a mine in their own backyard. One of the things that I'll invite many of you that are listening to this, many of you with experience of ethics and so on and so on, is there an ethics problem here of, on the one hand, governments demanding a future within EV vehicles, but then on the other hand, refusing to contribute to the production of the resources which would address that. Okay, so that leads me on to another issue, which as a geologist, I find quite important, I think. And I think this helps dictate some of the way in which we think about the future. So here we go. Here's a couple of projects here which state that they are zero emissions. So this is a zero emission vehicle. And the one thing that I'd say is that many people trying to get their heads around how we're going to go forward into clean energies in the future take these words as gospel. They think that there are no emissions associated with the use or the purchase of these vehicles. And of course, as a geologist, my response to that is at best misleading, and at worst, it is barefaced lying to sell a product. So let me explain why I think that. And here are some graphs from work done a few years ago. This is a published paper, 2016. This paper's got some limitations, but it's not a bad project of what they're trying to do. And what it's demonstrating here is the energy requirement to create a ton of total rare earth oxide, including yttrium, as a function of the ore grade. And what we find is that for many of the rock types around the world, we need to put in something like 1,000 gigajoules of energy to create a ton of total rare earth oxide. Now, most of our rare earths are coming from China, where the percentage of renewable energy is very, very low. So most of this energy has been created by the burning of fossil fuels. And in addition to that, we have, if you like, a CO2 generation equivalent for the reagents which are used to separate the rare earths from each other. And here again, you can see it's divided up by rock type. So carbonatite is one source, alkaline is another. And we can see that we end up generating something of the order of 50,000 kilograms of CO2. So in other words, 50 tons of CO2 for every ton of total rare earth oxide. And remember that the neodymium is only 10% of the total rare earth oxide. So that means that we are generating something like, up here, an order of magnitude higher, something like 500 tons of CO2 to create 1 ton of neodymium metal. And a typical wind turbine contains something like half a ton of neodymium. So the point that I'm making here is that we can do this in a variety of different ways. This is an analysis of different mineral types, and you'll notice that eudialyte, which is the source which we have access to in Europe, this is relatively benign in terms of the energy requirements, in terms of its total requirement to extract it, and the energy requirement to grind it and crush it up. These are relatively low in comparison with other rare earth ore types. But what is clear to me is that this is not zero emissions, that someone driving a neodymium-based car or a bus is not driving in a vehicle which has had no emissions to cause it to be created. Okay. So what can we do about some of this? And some of this is another aspect of research which we're doing here in St Andrews, is that we're looking at ways to reduce the carbon footprint of the extraction. And the point that I would make is that if we extracted our own materials in Europe, then we could control the energy requirements and reduce the energy requirements of the extraction process, the carbon footprint of it. So the way we're looking at this is what's called smart ore sorting. In other words, it's taking the properties of the ore as a function to try and find a way of automating the process of separation. And the sort of idea that we have is that we can use the physical properties such as colour, or in this case over here, luminescence, which is one which we think is particularly important. And what we're doing is we're developing ways to take an ore feed and a conveyor belt, have some form of automated detection process, and by using automated analysis of the ore as it goes past, we can use perhaps a jet of air to blow some parts of the ore away and keep the stuff that we're interested in. And if we do this before the processing, then we dramatically reduce the amount of energy that's needed to grind the rocks and the amount of reagents which are necessary to actually process them. So what basis are we doing? Well, we're using the automation of colour. So again, this is this mineral eudialyte. As we move around the deposit, actually the colour changes slightly. So we need to find ways which can identify a material which is demonstrably changing its colour as you move around from one place to another. And again, we found ways to quantify colour in a manner which means that they could be used by automated processing. And the other property which we worked on is mineral fluorescence. And many of you that have been to museums and things would have seen that many minerals fluoresce very, very intensely. And what we're attempting to do here is to use the fluorescence of the ore minerals as a way of identifying them on the conveyor belt. And so what we're doing is we're working here to develop novel spectroscopic methods, and particularly ones which can be used alongside existing conveyor belt technologies which are based around techniques known as X-ray transmission and X-ray fluorescence. And to do this, what we're attempting to do is to minimize as much as possible the carbon footprint of the processing of rare earth processing. So let me finish off then with coming back in a big circle and going back to what I started with, the slide I started with. We do know quite a bit about how rare earth and rare metal deposits formed, in other words, the geology bit, and every piece of research that we do improves our understanding all the time. A lot of my research and that of my colleagues and my students and my research group are focused on developing these, what we call genetic models. But as a geologist, what I see is a disconnect between the way in which we talk about green futures and very ambitious targets to reduce CO2 output from oil and gas, and the rhetoric that comes often associated with it, particularly the sense that mining is to be closed down. And I think that there needs to be a wake-up call about the practicalities of production there. Added to that, I think that, in my view, lacks unhelpful comments, that very unhelpful critique, are part of the problem. And zero emissions vehicles are a good example of that. They are clearly not produced without any emissions. Looking forward, Europe could, if it chose to, become self-sufficient in critical metals. There are world-class deposits waiting to be exploited in Greenland and in Scandinavia, but currently, politically, Europe chooses not to exploit them. But if we were able to, if we could control production, then we can introduce processes, legislation, which would minimize the carbon footprint of this production. At the moment, we're entirely dependent on the carbon footprint on other, which is taking place particularly in China, and the carbon footprints that entail. And that's about it. And if you have any questions, please let me know.
Thanks very much, Adrian, for making your paper so accessible to an interdisciplinary audience. I personally feel like I've learned a lot as somebody who doesn't know too much about physical sciences. I suspect you'll get quite a few questions, especially on the political context that you talked about towards the end there, and in your conclusions, which could be described as colonialism or coloniality. But there is a question already in the chat, so I'll just go straight to that because we've got about 5 or 6 minutes left. So Nick Hughes has a question. Would you like to read it out, or if not, I can read it out for you?
I think it was answered shortly after I put it in. It was asked, are there enough confirmed deposits extractable to deal with the expected demand for changing over to electric vehicles and wind turbines? I think you said yes.
Perfect. Job done.
Yeah, so I would say the answer to that is yes. I mean, back of the envelope calculations give us some sense of how much rare earth we can expect to extract from these particular resources that we worked on, but there are others in North America. The Western world is not short of these things. It's a case of really having the impetus and the will to turn them into something that's mined.
Fantastic. And James has put a comment in the chat.
Yep, so James's comment there, I think's entirely fair, which is that there is a discussion about life cycle emissions, how these go forward, and they're certainly not CO2 free without any, I think we all agree with that. But my personal view of it is that the language which it goes with them appears to be quite black and white, that bus is zero emissions, that car is a zero emission car. And my personal feeling is that when we speak to the public, that's not helpful.
I think we've got a question from Aliyah.
Yes, hello. Thank you so much for the presentation. Fascinating talk. I'm the one working in international relations, and I look at these issues about extraction of minerals. I work on the energy and oil and gas mainly. But from your talk, I also can conclude that there might be a dependent relationship, even if we develop those mines in Europe. Because UK at the moment, and if you look at from Scotland's Scottish perspective and the wind energy increase that we are seeing right now in Scotland, Scotland will also very much dependent on these ores coming from Europe, which is not a part of the EU anymore due to Brexit. So how, do you think there might be also a tendency from the European states to impose quotas that we have so far in China? And the other thing is that from the political perspective, I quite agree on the debate that there is a disconnect, and I see it myself. But one of these disconnects is also how much can we actually minimize this carbon footprint? So do you think that these kind of commitments, net zero commitments that are done by Europe to really minimize the emissions, that's the one that's holding up the development of those mines, or is it also mainly the financial aspect and the lack of investments and commitments from the government? Thank you.
Okay, so you asked, I think there are two questions. I jotted them down quickly. One was the fact that the UK is not part of the European Union. The UK doesn't have resources of this type. The geological constellation of events didn't quite happen in the UK, not in the way we needed. But you know, I think that we are politically allied, whether Brexit has damaged that alliance or not, I'm not entirely sure. But we are nonetheless politically allied towards Europe and towards North America. And I don't see a future evolving whereby we wouldn't be able to buy these resources from somebody in the Western world if we chose to do so. So I've tried to put this on a European perspective as a European, but I agree with you that there's a constellation of competing political issues there as well, not least of which is that Greenland is politically part of Denmark, but is actually a country in its own right, and it sometimes sees its vision much more allied to Asia in some cases than it does to Europe. So the Greenlandic people obviously need to decide precisely where they see themselves fitting into that. So that's the first question. The one about the minimizing the carbon footprint. Yeah, I mean, at the moment, the paper that I described to you, though there are many others which are attempting to estimate the carbon footprints of new technologies, some of these EV technologies. And the difficulty that they come up against is that the information is simply not available to them for some countries, and China is one of them. So they make guesstimates of what they think it must be to fill the void. And that means that we can't ever monitor it truly. We can't ever demonstrate whether it's coming down or going up or whatever. But if we were to take responsibility for these things, then sitting from where I'm sitting, then we can actually put into place strategies which actively seek to reduce the carbon footprint of that process. And it just strikes me as a logical pairing between the extraction and then the process restriction, you know, using modern technologies, green technology to reduce carbon emissions, and then finding ways to reduce those carbon emissions in the process of extraction.
Adrian, do you need to jet off, or have you got time for another one or two questions?
Yeah, it's 1 o'clock, isn't it? Yeah, I'm fine. Yeah, we can keep going. Yeah, I need to be away by about past.
No problem. Maybe we could just go a couple of minutes over, perhaps one or two more questions, if that's okay. So you got some nice feedback there in the chat from Peter Donnelly and Sean. Sean, is that more of a question or a comment? If you've got a question, feel free to take the floor. Is perhaps not. Perhaps not. There's a comment there, but
yeah. Okay. So actually, when I was thinking about what to say in my lecture, I could have bored you all with the minerality of eudialytes, which actually keeps me fascinated for years. But the one thing I would say is that I was trying to think of things and give you a perspective which would allow that communication to come between people like me looking at rocks and thinking about it from the rocks forwards, and people, as you'd say, looking at the ethics and the ethical questions of, on the one hand, insisting that we all go through carbon neutral futures, and then refusing effectively to come up with the resources to allow that to take place.
We do have one hand up, so I think there might be one more question coming in. I'm not sure if I'm pronouncing this right. George or Georg?
Yes, hello. Hello, thank you for the excellent talk, Adrian. I can totally relate to that. I'm also a geologist in background, and like the biased discussion on rare earth elements. So thanks for that. I'm wondering, you talked about the very energy intensive processing. Could you think of a viable resource which could, or let's say a sustainable resource which could be used to process these rare earth elements from the rocks?
Okay, well, I need to state straight away that this isn't my research field, the processing, okay. The actual processing and the chemistry and the wet chemistry of that. So I'm dependent on reading the open literature. What I understand is that eudialite potentially could be a lot easier to extract than many other minerals. And one of the things that's very, very difficult to quantify and put a price on is when we process minerals like monazite and xenotime, when we create uranium and thorium, what do we do with them? It's very difficult to put a price on that. And I would say that it's part of the environmental equation, even if it's not part of the economics. So I honestly feel that looking forward, yes, I think there is mileage to be made in better understanding some of these geochemical processes on some of these unusual minerals. We may find that they're easier to extract and they have fewer knock-on consequences than some of the more traditional routes using some of these other minerals. But of course, getting the investment, if you're an investor and someone came over to you and said, I want to open this mine, but it's based on a mineral that no one's ever successfully extracted before, would you invest in this mine, or would you invest in gold or iron where such problems don't exist? And I think that's part of the problem.
Great, thanks.
Okay, well, there's plenty of comments there in the chat, but it's approaching 5 past, and I'm sure that quite a few people have places to go. So if it's okay, I think we better leave it there. But I just want to say thanks again, Adrian. Really enjoyed it, and thanks to everyone so much for coming and for your questions and comments.
Yeah, great. Thanks a lot. Thanks for having me.